Hi everyone, thank you so much for logging in. I'm really excited to get to tell you a little bit about the work I've been doing for the past 6 years to better understand the causes and the consequences of the C plus deficit in a set of local universe star-forming galaxies. Before I jump into my research, I wanted to take us on a little journey through a star-forming region in our own galaxy in the Orion Nebula. So all of this is based on Hubble imaging. So we're going to be looking at optical light, a kind of optical light model of the Orion Nebula, the star forming region. And as we fly through this star forming region, I want you to notice a few things. First of all, as we go through, the thing that might immediately jump out to you is there's quite a lot of these red clouds in this region. So that is hydrogen gas that's emitting H-alpha light that looks red. So we can see this ionized hydrogen gas surrounding these recently formed stars in our own galaxy. As we start to head towards the center of the Orion Nebula, you'll start to notice that there's less hydrogen gas, but quite a few of these really bright white stars. So these are the baby stars in this star-forming region, the recently formed stars. They look really white here because they're very hot and young. They tend to be, this is where we see the brightest stars, as in recently formed stars. If we could see in ultraviolet, we would see them also very bright in the ultraviolet. As we begin to head out of this cloud, out of the Orion Nebula, we'll see more of that hydrogen gas, those red clouds, but you should also look out for some dark regions in this nebula. Now, those aren't places that there aren't stars or gas. It's places where there's dust in this region as well. That dust might be blocking, absorbing, scattering the light from the stars, especially this optical light. So making the regions look dark, despite the fact that it's this quite energetic area surrounding these recently formed stars. So as we leave, we'll get one glance back at this beautiful star-forming region we just flew through. And just so want you to keep in mind that idea of young stars, gas, and dust in these star-forming regions as we discuss my research. If you're curious and you want to go out and see the Orion Nebula, you can if you're in the Northern Hemisphere, which I think everyone here is. So if it's a clear night, right now Orion is up in the early evening. So if you can find those 3 stars of the belt that form the belt of the Orion constellation, the Orion Nebula is right below the middle one in this kind of sword type structure in Orion. And another cool thing is that if we could see in the infrared, as I mentioned, if we could see in the UV, it would look different. It would also look quite different if we could see in the infrared. This is what Orion would look like if we had infrared vision. So now that we've gone on that journey, we're going to start another journey with a quick tour of extragalactic astronomy, kind of what we know and how we know it. Then I'll get into my own research with a definition of the C plus deficit, as well as a description of why it's a problem worth solving, how I try to solve it using the Kingfish and BTP samples and data, how I use those samples to isolate C plus emission by ISM phase, and how I use that isolated C plus emission to test different causes of the C plus deficit. Finally, we'll wrap up with some conclusions as well as time for questions. Fingers crossed. So first of all, like I said, we're going to start with a kind of whirlwind tour of extragalactic astronomy. And as I begin this tour, I wanted to start with an image of one of the galaxies from my sample, NGC 7331. So that's this big galaxy right here that we can see kind of looks like what we might think of when we think of a galaxy. So it's got kind of a flat disc shape. It's got lots of different colors, some blues, yellows, and reds. And it also seems like it's kind of on its edge, but we can see that there's some spiral structure as well. So this is kind of the quintessential vision of a galaxy, but not all galaxies look like this, and understanding the differences are really important. And so this is why I chose NGC 7331, because it's got quite a few background galaxies that don't look like this kind of quintessential spiral galaxy. We can see one up here. These are actually called the fleas surrounding NGC 7331, but they're background galaxies, where one up here and this one here don't have those nice blues, and they look like they might also be missing the spiral structure. So understanding why galaxies look the way they do and how we get to the universe today is a big part of extragalactic astronomy. So first off, let's just ask, what do we know about galaxies? One of the major things, the first thing any intro astronomy student is going to be taught is that galaxies tend to come in three different types. So we have those spirals, which was what NGC 7331 is, what is shown here with M101. It's kind of what we think of when we think of a galaxy. Our own Milky Way galaxy is a spiral galaxy, where we've got this spiral structure. It's pretty flat, kind of disc-like, and we see lots of pretty colors, blues, reds, and yellows. Spiral galaxies have those pretty colors because they have continued forming stars. So even the ones we see today are still forming stars, and we can see light from young stars in these galaxies. On the other hand, we have elliptical galaxies, which don't really have those blues or reds, and they don't tend to have much of that spiral structure either. So these aren't flat, they tend to be more ellipsoidal or football shaped. And extragalactic astronomers often call them red and dead because they don't have that blue light, they don't have any young stars. So something happened in the history of this galaxy ESO 325G004 to tell it to stop forming stars. Something happened and it is no longer forming stars, while M101 has continued to form stars. The last type of galaxy shown here is this irregular galaxy. It's anything that doesn't really fit into the box of elliptical or spiral. They tend to be fairly small, so a lot of dwarf galaxies are irregular galaxies, and they often have bursts of star formation. So what you might have noticed as I described the different types of galaxies is that outside of the differences in how they look, all of them also have fairly significantly different star formation rates. So how these galaxies are forming stars is some of the big thing that drives the differences in these three different types. And understanding why one galaxy might have stopped forming stars and another has continued is a big question in extragalactic astronomy. So for most of this talk, I'm going to be focusing on spiral galaxies because I'm interested in star formation, and my sample has mostly spiral galaxies. So I'm going to kind of use that as I continue on this tour of extragalactic astronomy. So if we look inside of a galaxy now, thinking more on an individual galaxy level, we can break the components of a galaxy down into four main parts: stars, gas, dust, and dark matter. I'm also not really going to talk much about dark matter because it's not part of my research, but pretty much every galaxy we look at seems to exist in a large halo of this dark matter that doesn't interact with light at all. And we can tell that it's there based on how it gravitationally affects the three luminous components, the stars, gas, and dust, which do interact and emit light. So we can learn more about those three luminous components by looking at light from a galaxy and by breaking that light or electromagnetic radiation down into different wavelength bands to see different parts of a galaxy. As an example of that, this is M51, the Whirlpool galaxy, looking at different wavelengths. And what we can see is as we shift from longer to shorter wavelengths, we're looking at different parts of the galaxy. So here at the long wavelength end, looking at radio wavelengths, really long wavelength light, we're seeing kind of cold gas, carbon dioxide emission from this galaxy. As we get shorter, starting to look in the infrared, we're seeing more hot dust, some old stars, and we see slightly different structures than when we look in the cold gas. If we look in optical, the kind of light that we see, we're seeing kind of older stars, middle-aged stars, stars like our sun. And again, the similar structure, but we're seeing again kind of different areas are brighter when we look in optical because we're tracing a different part of the galaxy. And then as we get to even shorter wavelengths we can't see because they're too short, ultraviolet and X-ray, so really high energy, ultraviolet coming from young stars, and then X-ray coming from extremely hot gas. So by breaking the light from a galaxy down into different wavelengths, we're looking at different components of that light, of that galaxy, and we can get a better idea about what's happening inside. And so thinking of that, we can start to break down the galactic ecosystem into different parts, with some of those parts being like the Orion star forming region that we flew through, and other parts being more diffuse gas. So as we dig into what's inside of a galaxy, we first want to define the gas and dust that's between the stars as the interstellar medium, or the ISM. So the stuff between stars is the interstellar medium, which I will call ISM throughout this talk. we can take the ISM and we can further divide it into different phases based on the ionization state of hydrogen in that phase. So hydrogen is the most prevalent element in the universe, so it's a good way to kind of gauge the different conditions inside of a galaxy based on what hydrogen is doing. So we have ionized phases of gas where hydrogen, that proton and electron, have been ionized, so we have just free protons and electrons flying around. We have neutral phases of the ISM where hydrogen is existing in its atomic state, so we have the protons and electrons bound together to form atomic hydrogen. And then we have molecular phases of the ISM that are cool enough that those hydrogen atoms have formed diatomic hydrogen, two hydrogens bound together, or are parts of other carbon and oxygen, typically molecules. When we think about, since I'm interested in star formation, I've kind of highlighted what these different phases look like around a star forming region. So this is similar again to that Orion Nebula that we flew through, where in the center we have those young stars that have maybe cleared out some of the gas with their high energy light. So in the Orion Nebula, there were those bright white stars. In this one, we're just representing it with one hot blue O star. As we get out, we eventually reach the H2 region. So these are those red clouds of gas that we saw in the Orion Nebula. It's where hydrogen is ionized. It's emitting a lot of H alpha radiation. Things are really hot because we've got all this inputted energy from our young stars that tend to be really bright and really hot. Eventually, though, we run out of radiation from these young stars that can ionize hydrogen, and we enter what we call a photodisassociation region, or a PDR, which is one of our neutral phases of the ISM. So here, hydrogen is neutral because there's no more photons that can photoionize those hydrogen lines. We've run out of high energy photons, but we still have quite a bit of high energy radiation from these young stars. That's just not high enough energy to ionize hydrogen, but can ionize other elements as well as kick electrons out of dust particles and heat things up in its own way. Finally, here, this is showing the cold phase that's going to be outside. Eventually, we're going to exhaust even the kind of mid-range energy from the star, and we'll end up in a colder phase of the ISM, where hydrogen will be predominantly molecular. And this phase is also really important for star formation because this is where the gas that will eventually form stars comes from. So it's dense enough that we can get the conditions where we might form stars. So for this talk, again, for my research, I'm interested in star formation. So I'm really interested in these kind of two phases here, the ionized H2 regions surrounding recently formed stars, as well as the slightly cooler neutral PDRs surrounding those H2 regions. If we want to measure star formation rates, so understand what's happening in those star forming regions, there's quite a lot of reasons why we might want to do that. So hopefully I've already highlighted some of them. Star formation rates seem to be one of the main differences between those three types of galaxies. Star formation is also kind of what drives galaxy evolution and enrichment as well, through something that we call the baryon cycle, or the star-gas-star cycle, which is represented here. So we start with kind of our diffuse atomic hydrogen clouds in a galaxy, which, if they get dense enough, cool enough, can form molecular hydrogen clouds, which can get to a point of gravitational instability where we start getting collapse of that hydrogen to form young stars, creating star-forming regions like the Orion Nebula, which we flew through. Inside of those star-forming regions, we have young stars, which are creating energy by fusing hydrogen and helium into heavier elements like carbon, nitrogen, and oxygen. So all the carbon and nitrogen and oxygen that makes us and everything on our planet up was once in the center of a young star, getting fused from the hydrogen that we get from the Big Bang. So how galaxies form stars are really important if we want to think of the chemical enrichment of a galaxy, how we get elements above hydrogen and helium. Eventually, those stars will die, especially the really large hot stars, which don't live for very long. And those deaths will either be explosions called supernova, which will again enrich the gas by outputting that carbon, nitrogen, and oxygen that was fused in the center of the star into the ISM, resupplying the ISM with more heavy element enriched gas, or through smaller stars becoming planetary nebula, shedding their outer layers that will be enriched again, and resupplying the ISM with gas that can start the cycle again. So understanding, being able to measure star formation rate is really important if we want to understand how galaxies grow and change with time. And the main way we measure star formation rate is by looking at signs looking for signs of really hot O and B stars, really hot, really bright O and B stars that don't live for very long. So if we can find those O and B stars, we know there must have been recent star formation, because otherwise they would have all exhausted their supply of gas and died. So the way we look for O and B stars is by looking for really bright, high energy light. So things like UV light or H alpha emission. And so as an example, this is NGC 300 in optical light, and then shifting our wavelength range, so we're only looking at H alpha light, we can see that there are some really bright star forming regions that stand out in NGC 300. So this would be a sign that there's star formation happening in these bright H alpha clumps, and we can use the brightness of that H alpha to predict how many stars recently formed in this galaxy. Unfortunately, if we're trying to measure star formation rate, the dust in the ISM becomes a major issue. So the way I like to think about this, or one kind of recent example that many of us lived through this past year, dust in a galaxy is actually pretty similar to smoke. So it's really small, kind of carbonaceous silicate or carbonaceous grains. So kind of similar to smoke from a wildfire. And last fall in the Pacific Northwest in California, Oregon, and Washington, when we had those fires, you might have noticed the sky turned red. And that's because the dust in our atmosphere was absorbing or scattering the blue and yellow light, the shorter wavelength light, more than red, longer wavelength light. So we saw the blue and yellow and green lights getting blocked, whereas the red light was able to pass through. The longer wavelength, lower energy light was able to pass through. And the same thing happens in galaxies. So dust in a galaxy is going to predominantly block shorter wavelength optical and UV light, and either absorb or scatter that and re-emit it in the infrared. So this is an example of a dust cloud inside of our own galaxy, where we can see if we look in visible light, it looks like an empty region in space. But if we shift our gaze to look in infrared portions of the spectrum, we can see through it. Dust can, depending on the galaxy you're looking at, dust can re-radiate up to almost 100% of the energy from a galaxy. So if we're not taking into account dust blocking the UV and optical light, that H alpha light is in optical, then we're going to be underestimating our star formation rate in a galaxy. So we need to take into account attenuation from dust in our UV and optical star formation rate indicators. This is typically done by looking for signs of hot dust, so dust heated by young stars, which is going to be essentially infrared light. And this becomes really important if we want to understand how galaxies evolve over time in something called this, which is typically shown in something called the cosmic star formation history, and is what is shown here, where we're plotting the star formation density. So we're seeing more active star formation, less active forming star formation, and we're plotting that as a function of time in universal history, with 0 being today and this kind of 13 being pretty close to the Big Bang. So these are kind of the first galaxies that we can see. And this shows us, and this is before, if we haven't done dust corrections, we can see that depending on how you measure star formation rate, you're going to get very different results for what this curve looks like. And this becomes really important in the early universe, where we only have a few indicators of star formation, and all of them tend to come from the ultraviolet. So after we correct for dust absorption, we get this nice curve here where the data points actually match up. But again, these points over here, it's more uncertain to tell how we should be correcting for dust attenuation, because we don't have a lot of data for these really early universe galaxies. But understanding this curve, why we see this peak in star formation about 10 billion years ago, what was happening here? Is there really this steep fall off? Why are we going to continue on this downward trend today? Are all really important questions for extragalactic astronomers. And so if we could find a way to measure star formation rate that didn't depend on dust attenuation, that would be an awesome way to get a better idea of this, and that could be done both in the early universe and today. We could get a better idea of what this curve actually looks like. So just as a quick summary, that was a really fast fly through of everything we know about galaxies. or a subset, everything you need to know before we get into my research. But just really quickly, galaxies are awesome, and kind of the original definition of the word awesome. They contain stars, gas, dust, and dark matter, which we can measure the different components by looking at different types of electromagnetic radiation. By looking at those different forms of electromagnetic radiation, we've been able to subdivide the gas and dust that forms the interstellar medium inside of a galaxy into different phases based on the ionization state of hydrogen. And we've also been able to measure star formation rates in galaxies that are a really important indicator of how a galaxy is growing over time, but have this issue of dust absorption and attenuation that we need to account for. So this is where the C+ line comes in. So C+, this anytime I'm going to try to stick with C+. I might occasionally say C2 as well. It's the same thing. I'm sorry. But C+ is a emission line from singly ionized carbon. So that's what this 2 means. It means our carbon has had 1 electron ejected from it. The C+ 158 micron line is a really bright emission line of singly ionized carbon, which we can tell by looking at this star-forming galaxy spectra, where we have brightness on the y-axis and wavelength on the x-axis. And we can see this carbon line pops up really high in terms of brightness for this star-forming galaxy. We can see the H-alpha line from star formation is over here. The carbon line is brighter than that. So the C+ line, like I said, it's a emission line from singly ionized carbon, and it's often the brightest observed emission line in star-forming galaxies. So why might be a little strange that it's the brightest when we have so much more hydrogen, but that's because one, carbon is still one of the more prevalent elements in our universe, so it's the 4th most prevalent element after hydrogen, helium, and oxygen. Ionized carbon tends to be the Singly ionized carbon tends to be the predominant form of carbon inside of the ISM because carbon has a pretty low ionization potential. So we can get it both in ionized and neutral, as well as even a little bit in molecular phases of the ISM. We'll see ionized carbon, even though the ionization state of hydrogen is changing. Carbon-2 also is very bright because of its very long wavelength. So 158 microns, this is in the far infrared portion of the spectra. And what that means is that the carbon-2 line can blast through gas and dust with very little attenuation. Pretty much no attenuation unless you're in an extremely dusty galaxy. So we're seeing all of the 158 micron emission. We can see we don't have to worry about correcting for dust attenuation if we want to measure the brightness of this line. And so this brightness of the C+ line make it detectable both in the local universe as well as in really high redshift, the distant universe galaxies. So as an example, these are some Atacama large millimeter C+ detections from redshift of 6 quasars, and it's only a handful of what has recently become available through millimeter arrays. So if we could use carbon-2 to measure star formation rate, we could kind of make that cosmic star formation history using a single tool, so this carbon-2 emission line that's detectable both in local and high redshift universe and doesn't need to be corrected for dust attenuation. So this would be a really great way to measure that star formation history if we can relate carbon-2 emission to star formation rates. Now, there is some reason to believe that we can, and that's predominantly because carbon-2 is one of the major cooling lines of the ISM. So what this animation is showing is kind of the typical conditions where we might see C+ emission. So we have this is kind of our PDR surrounding our young stars. So back in that Orion Nebula, these were those white stars in the center. We have our H2 region represented by these dashed lines, and then our PDR shown in this kind of more solid gray. Carbon-2, C+ will exist both here and here, so it's all over the place. But as young stars heat up our gas, put out a lot of high energy ultraviolet radiation, that will cause electrons to be ejected from grains, that will heat up the gas, cause collisions, that eventually might bump into singly ionized carbon, exciting the 158 micron line. So, which can then carry energy, take kinetic energy and carry it out of the ISM through radiation. So carbon-2 is cooling down the gas. by radiating out this light that doesn't get absorbed by dust. So the reason why this mean carbon-2 might be a tracer of star formation rate is that young stars are one of the main things heating up the ISM. So if young stars are heating the ISM and carbon is cooling the ISM, and our ISM is pretty close to thermal equilibrium, so heating is balanced by cooling, we would expect the strength of the carbon-2 emission to be directly proportional to the number of recently formed stars or the star formation rate. Unfortunately, there seems to be more to the picture than this. There's something else going on that makes it so either we don't have a thermally balanced ISM or something else is causing the carbon-2 luminosity to proportionately decrease as we go to more actively star-forming galaxies. And this is the effect known as the C+ deficit, and it's this problem that I'm trying to solve. So the C+ deficit is what is represented in this graph, where we have the ratio of C+ luminosity to total infrared luminosity as a function of star formation rate surface density. So just star formation rate divided by area. So less actively star forming, more actively star forming, and then we have this proportional C+ to TIR, total infrared luminosity. And what should immediately jump out is that as we go to more actively star-forming galaxies, this ratio decreases, which is a problem because TIR emission, total infrared emission, traces hot dust, and so is often used as an indicator of heating in a galaxy. So if TIR is tracing heating and C+ is tracing cooling, and we have our thermally stable ISM, we would expect this line to be flat. So we would expect this ratio to be consistent regardless of star formation rate. Clearly, that is not the case. We can see this decreasing trend with more active star formation. So if we don't understand why this trend occurs, why we see this decrease, we cannot use C+ to measure star formation rate. And we clearly don't have a complete understanding of the thermal regulation processes happening in the ISM. So I want to figure out why is this deficit happening, and could it be corrected for, and then could we use C+ to measure star formation rate? So those are some of the big questions I'm trying to answer by investigating the C+ emission as well as other types of emission from the Kingfish and BTP samples. And this is just one of the Kingfish galaxies, IC342 in infrared. So just a really quick overview of these two surveys. So Kingfish stands for the Key Insights in Nearby Galaxies, a Far Infrared Survey with Herschel. And so this was a nearby galaxy survey completed with the Herschel Space Observatory, which is a far infrared telescope. And it looked at the goal of the Kingfish project was to better understand the thermal properties of galaxies at a wide range, at a kind of across different types. So looking at both ellipticals and star-forming galaxies. It targeted 61 nearby galaxies using the far infrared photometry and spectroscopy available with Herschel. Only a subset of those have the full wavelength range that I need to perform my analysis. So those are the ones indicated with green stars. And you'll notice that those all tend to be spiral galaxies. So they're all star-forming galaxies. So I don't have any ellipticals or dwarfs in my sample. All of the galaxies in the sample are, like I said, they're pretty nearby. So the furthest ones are about 30 megaparsecs away, and they all have pretty typical metallicities. So typical amounts of heavier elements for nearby galaxies. BTP was in a follow-up survey. It stands for Beyond the Peak. So I'll discuss that in a second. The two big things I need to perform my analysis are our spectral maps of the C+ and nitrogen-2 205 micron lines. And I will talk about why nitrogen-2 is important in a second. But so from the Kingfish survey, there were 31 star-forming regions in 28 of the galaxies that were mapped at both of these two infrared lines. And the star-forming regions look like these kind of green squares shown here, where we have nuclear star-forming regions centered on the middle of the galaxy, or extranuclear star-forming regions shown by these two small green squares in NGC 6946. We can see that the the green squares represent where there was PAX spectrometry at 205 microns from the Kingfish survey. So it's pretty small, pretty much just those star forming regions. So in order to also get information on the more quiescent ISM surrounding these star forming regions, Beyond the Peak followed up on a subset of those 20 of those regions, mapping them with the wider field of view Spire instrument on Herschel to get the quiescent areas around star forming regions. With the information from the carbon-2 and nitrogen-2 lines, we can separate the carbon-2 emission by ISM phase to get an idea of where maybe the C+ deficit is having the greatest effect. So like I said, carbon has a pretty low ionization potential of only 11.3. Like I said earlier, carbon has a pretty low ionization potential. So it's 11.3 electron volts, which notably is below 13.6 electron volts needed to ionize hydrogen. So we can see singly ionized carbon both in H2 regions surrounding young stars, as well as in the neutral PDRs surrounding those H2 regions. So if we really want to understand where and when and how the deficit occurs, it would be helpful if we could see how much of the C+ emission was coming from an H2 region and how much was coming from a PDR. So we could kind of see what conditions are necessary to cause the C+ deficit. The nitrogen-2 line is an ideal tool for answering this question because nitrogen has a higher ionization potential than hydrogen at 14.5 electron volts. So again, higher than that 13.6, which means singly ionized nitrogen can pretty much only be found in ionized phases of the ISM, like the H2 regions. So we can use the expected ratio of C+ to nitrogen-2 emission to predict how much of our C+ emission was coming from the same areas in the ISM as the nitrogen-2 emission, and how much was coming from the neutral phases where we're not seeing any nitrogen-2 emission. And so that's what's shown in this plot here, where we have the expected ratio of C+ to nitrogen-2 205 micron emission shown as this solid cyan line. And we can see all of my data, which is the C+ to nitrogen 205 data, fall either on one case or above this line, which tells us that a large fraction of the C+ emission in pretty much all of my regions is coming from those neutral phases where we don't see any nitrogen-2. So if all of these data points were on this line, we could say that the C+ emission was all coming from the H2 regions where hydrogen is ionized. Because it's falling above, we know some of it must be coming from the neutral phases. And we can use how high above this line these points fall to predict what fraction of that C+ emission is coming from the neutral phases. Just really briefly, I'll point out that the other option, so we're using 205 micron detections. You can also use 122 micron nitrogen-2 lines, but we choose to use 205 because the nitrogen 122 to the C+ to nitrogen 122 micron ratio varies quite a bit as a function of electron number density. So depending on what your ISM conditions are, this can kind of cover an order of magnitude in terms of what we expect this predicted ratio to be, whereas the C+ to 205 micron line is pretty much for no matter what your ISM conditions are. So with this data, I split up my C+ emission and was able to look at the deficit in the individual phases of the ISM. So first here, this was one of the major results of my 2019 paper. The first panel here just shows if we don't subdivide our C+, what does our deficit look like? And we can see there's a slight deficit, but there's not much of one. So as we go to, here I've plotted versus the 70 versus 160 micron ratio, which I've shown here indicates hotter dust or more active star formation as we move to higher values. And so there is a slight deficit, there's a slight decrease in the C+ to TIR emission, but there's not much of one. This is essentially what we expect for our sample. We're looking at normal star-forming galaxies. We don't have any star-bursting galaxies, no ultraluminous infrared galaxies or ULIRGs, no AGN, and no high redshift star-bursting galaxies. So we kind of expect a deficit, but not much of one. So this is essentially what we expect for our sample. What's more interesting is what we see when we divide our C+ emission by ISM phase, looking at the ionized phases of the ISM, where both C+ and N2 are present, and the neutral phases of the ISM where only C+ is present. And what we can see is in the ionized phases, there's a very clear deficit trend, whereas in the neutral phases that almost completely disappears and we have that flat relationship that we would expect if C+ was tracing cooling, which was tracing heating. So this was the first indicator that whatever is causing the C+ deficit in our galaxy, in our star-forming regions, seems to mostly be occurring in the ionized phases of the ISM and can maybe be completely removed if we only look at the neutral phases. The other part of this paper was, of my 2019 paper, was to test whether or not the C+ emission from a single phase of the ISM might be a better star formation rate indicator than C+ emission from the total, from both phases, both the neutral and ionized phases of the ISM. And that's what's shown here, where we have our total C+ emission, our ionized phase C+ emission, and our neutral phase C+ emission, luminosity plotted versus star formation rate measured with the composite FUV plus 24 microns, so ultraviolet corrected for dust with infrared emission. And we can see there's not a huge difference between the total C+ emission and the neutral C+ emission star formation rate indicators, because most of the C+ emission comes from the neutral phases. So about 60 to 70% of our C+ emission is in the neutral phases, so there's not a huge difference here between total and neutral, so we didn't get a better indicator of star formation rate. But again, what's kind of interesting and what was unexpected for us was how poorly the ionized phase C+ emission did at tracing star formation rate. So we had originally thought that like maybe the C+ emission from just the H2 regions surrounding star formation rate could be a really good indicator of star formation. But we can see there's this very large scatter when we look at only the ionized phase C+ emission. And that's probably due to that difference in where we see the deficit behavior that I showed in the previous panel. So my next step was like, I saw this and I wanted to understand why is there this really clear difference between the ionized and the neutral phases of the ISM? What's happening in the ionized phases to cause this large deficits in our sample? So in order to do that, the first thing I wanted to do was to make sure that we weren't somehow messing something up by only dividing our C+ emission by ISM phase. And so going back and taking my that fraction, that C+ to TIR, and dividing not only the C+ emission, but also the total infrared emission by ISM phase to better understand where the C+ deficit is occurring. And so I do that by using the Segal spectral energy distribution program, which is a spectral energy distributor. So it takes photometry from a galaxy shown by these kind of blue squares for NGC 7331, that galaxy I showed way back at the beginning. So these are the photometric detections, so just how bright it is at different colors, and fits a spectra, this black line, this black curve, so how much light is emitted at every wavelength, to that photometric data. Segal uses a energy balance to determine how much to fit these spectra, so it's balancing how much emission in the infrared we see with how much attenuation there should be in the UV. And then it's able to tell us what the kind of dust properties, gas properties, and stellar properties of each star forming region are. And we're able to use that data to predict, along with the DRAIN 2007 dust models, to predict what fraction of the dust luminosity is coming from the H2 region surrounding recently formed stars. And we do that using this semi-gnarly equation shown here, where we have the fraction of the dust luminosity, so the fraction of our infrared luminosity, that is coming from regions irradiated by an interstellar radiation field U greater than some cutoff value. So we're looking for dust that's been radiated by light that has a higher energy than some cutoff. And so what we can do is we can set our cutoff value to what we expect the radiation field to be at the Stromgren radius, or the radius of our H2 region, to pull out the fraction of the dust luminosity that's coming from inside the H2 region and compare that to the fraction coming from without. So with that, we're able to look at the C+ to TIR emission from the individual phases of the ISM. So now I'm dividing not just my C+ emission, but also my total infrared emission by ISM phase. And one of the first things I wanted to test was whether or not thermalization of the C+ line in ionized phases of the ISM could be causing the deficit behavior we see in our sample. So just a really quick definition, thermalization is what occurs when we essentially hit a ceiling in the amount of C+ emission we can get from a region. So if you remember back to that animation, we got C+ emission when singly ionized carbon was bumped up to a higher energy state and then fell back down and radiated light. Eventually, with thermalization, you'll hit a point called the critical density, or N crit, where all of our carbon is bumping up and going down as fast as it can. So we can't, adding more energy, more electrons into the ISM won't create more C+ emission because we've kind of maxed out the amount of C+ emission we can get for our H2 region. And so this would cause a deficit because we're kind of seeing C+ holding steady while TIR would continue to increase as we input more energy into the ISM. And what was really exciting was that when we plot our C+ to TIR from the ionized phases of the ISM, those H2 regions, versus electron density, we show the critical density as well as the theoretical predictions for what thermalization would look like. Our data follow these theoretical predictions pretty well. So there's no fitting done here. This is just theory compared to data, and our data seem to be pretty flat until we hit the critical density and thermalization occurs, and then they start to decrease. So this was a sign that thermalization within the ionized phases of the ISM could be causing that deficit that we observed in our ionized C+ emission. Just a quick note, when we look at the neutral phases, so those PDRs, for our sample, we don't reach the critical density within the PDRs, so we don't expect C+ from neutral phases to be thermalized. We just expect to see this in the ionized phases, which means that we can only, thermalization in H2 regions can only really explain the moderate deficits that we see because ionized phase C+ emission tends to only be 20 to 30%. So we can't get huge deficits based with only thermalization. But if we know that thermalization is affecting our C+ emission and we know how it's affecting our C+ emission, we can then correct for thermalization and see how that affects our C+ to star formation rate indicator. And so I should say, this was the result that came out last week still in my most recent paper in monthly notices. So this is follow-up work on that, where we could see if we correct our C+ luminosity shown on this x-axis for thermalization. So we have our uncorrected C+ plotted versus star formation rate, where we have quite a few points that are, the C+ is under predicting star formation rate. So C+ is, we have star formation rates higher than we would expect for the given C+ luminosity, so essentially the effects of the deficit. If we correct those points for thermalization, they get shifted over, shown here, and fall almost completely on our line of best fit. So this is an exciting result that shows if we could correct for thermalization in H2 regions, at least for modified deficit, we can correct for at least for modest deficit behavior. Like I said, though, this thermalization can only really explain modest deficits. So there's probably other things going on in ULERGs, AGNs, more star-bursting galaxies where we see the greatest deficits. So even though I don't have any of those in my sample, I wanted to go through and see how 7 proposed causes of the deficit, so thermalization plus 6 others, might be affecting the C+ to TIR ratios that I measure for my isolated ISM phases. And with this kind of analysis, I'm able to pretty much qualitatively rule out the effects of dust absorption, self-absorption of the C+ line, higher fractions of doubly ionized carbon, as well as O1 becoming the predominant cooling line in my regions. The one thing we see that is semi-interesting is that when we look at the C+ to TIR for the neutral phases, so those PDR measurements, and we plot that versus the photoelectric heating efficiency in our galaxy, there's a pretty clear trend shown here, which is similar to what the goals and shining sample are suggesting is the main cause of the deficit for their ultraluminous infrared galaxies and AGNs. They're saying changes in the photoelectric heating efficiency are changing our C+ to TIR ratio. So this is, even though we're not seeing the large deficits here, there does seem to be a pretty clear dependence. This ratio does seem to very clearly depend on how efficient the photoelectric heating is in the ISM. So coming to the end here, just to really quickly wrap up some of what I found and mention some of what I hope to do in the future. What I hope to do in the future is what is essentially shown here. Sorry. Which is the LMC. So this is, I want to continue my analysis of C+ emission into more actively star-forming regions and also lower metallicity areas that are more similar to some of the early galaxies before we have chemical enrichment. So the LMC, the Large Magellanic Cloud, one of the Milky Way's satellite galaxies, along with this Small Magellanic Cloud, the Milky Way's other satellite galaxy, are ideal laboratories for this because they have very actively star-forming regions that we can kind of see in the LMC with these bright H-alpha clouds. And they also have very low metallicity. So if we could measure the C+ emission, use kind of similar tools to see where the C+ deficit is happening in these galaxies, we get something that's more comparable to those early universe galaxies where we saw the really high deficits. And just really quickly, some conclusions. For the normal star-forming galaxies that I investigated, we found the C+ deficit mostly occurs in the ionized phases of the ISM, which could be tied to the thermalization of the C+ line in H2 regions, which then if we correct for, we can get potentially a better star formation rate out of our C+ luminosities, and should be considered as we analyze the wealth of high redshift data, high redshift C+ data. With that, I would like to thank my committee, especially my advisor, Danny, without whom none of this would have been possible and I probably would have quit grad school. So just a huge thank you to him. And then also to the NASA Earth and Space Science Fellowship, along with the Wyoming NASA Space Grant for funding my work, the Herschel Space Observatory for providing the data, and the wonderful Kingfish and WeGoat teams for supporting me on my journey. And just very briefly, I want to stick in and also give me a little boost before I have to go into the committee only section. It wouldn't really be a talk about my time in grad school without some mention of the power of active learning and how we can assess different active learning tools. So this is just a quick example of one assessment where I ask students in an introductory astronomy course to come up with an experiment to determine what stars are, both on day 1 of a class and on the last day of a class after doing a lot of activities and active learning throughout the course. And what we can see is that on the first day, we see words like constellation, stuck, light, observe, compare. I think so, good words, but not necessarily astronomy words. Whereas on the last day, we see the word spectra, spectrum, luminosity, parallax is on here somewhere, there it is, emission and absorption. So just words that very much are tied with astronomy and might be good if we wanted to answer this question. So just an indicator that active learning can work and we should continue to do it as we teach astronomy. So I'll go back to my conclusions and I will do my best to answer any questions that you have. Thank you.